I guess it's theoretically time for the meeting to start, but I think we'll wait a few more minutes for some more people to show up. Hi, everybody. I guess we will go ahead and get started. We can take a few minutes to get through the initial administrivia in any case. Maybe some more people will show up during that. Let's see here. This is the Notewell, which presumably people have seen a lot before. I'm so I guess I should. Here I'm Donald Eastlake with FutureWay. And this is the Babel Working Group meeting at IETF 111. So this is the Notewell. You should note this. In particular, if you're aware of IPR in anything you present, you need to inform people about that. That's intellectual property rights. Also, I'd like to remind people that reviewing documents is a good thing to do. If you want to get your documents reviewed, it's good to review other people's documents, and reviews increase the quality of the documents. This is the proposed agenda for this virtual meeting. So we're in the agenda bashing point here. The way it would be very useful to have somebody who would be a clerk or a scribe to take minutes for this meeting. There is a shared writing area that everybody can get at, so people can cooperate on that sort of thing. and help out with the minutes. But the current proposal is that there's a status of files and chairs report, and there's one slide in there on the current state of the Yang model, which Mahesh is on the call, so he can speak to that one slide in that presentation. Then I have a presentation on reviving Babel RTT by Julius. And we have time available. I've put together a presentation which may be of interest to people. It's somewhat layer 2 oriented about addressing in Wi-Fi transit link. It's supposed to be transit. It says transit. That should be supposed to be an N right there. It's a typo. Multicast and stuff. And then we'll wrap up. So anybody have any suggestions for additions, deletions, or changes or the like? Let's see. Okay. Looking at the chat, not hearing suggestions for changes. I guess we can proceed with this agenda. The next item, let's see. Would be bad taste to ask that agenda bashing be removed from the agenda. Well, you know, it's like tradition, so I don't know. I mean, if somebody wants to change the agenda, they're certainly entitled to make that request and speak up. So, but in any case, document status. We have 5 RFCs that are the output of this working group, including the Babel routing protocol. These replace the previous experimental ones, and they also now include the Babel information model. I see that, actually see Barbara is now on the call. Since she has taken notes a lot in the past, I was wondering, Barbara, would you be willing to take some notes for this meeting as well?
I just got on, sorry.
Yeah, that's fine. All right, no problem.
Yeah, I'll do that.
Great. And it's this using the share writing tool, other people can assist. So, continuing, I guess, with the document status, we have the source specific is in auth 48, and so Julius has responded to all that. Hopefully that will come out. Might even come out this week. We shall see. There's the Yang model, which is in IESG Discuss, and there's a slide right after this on that. The Babel IPv4 via IPv6 is in publication requested status, so that needs to be reviewed by our AD. There is the expired RTT extension, which Julius will be speaking to. And there's the HomeNet Babel profile is currently waiting on the source specific. So when source specific goes through, then that should eliminate the block on that, which is in misref. And there has been a beer extensions draft published. So this is on Babel Yang model. Would you like to speak to this, Mahesh?
Can speak to that. Are you able to hear me?
Yes, I can.
Good. So, Donald, your status said that the Babel Yang model document is hopefully not discussed. We should have addressed most of the discuss. There are some comments though that are still left. So it is an ISG review, and most of the comments have been addressed. There is one outstanding set of comments from Ben, which I am in the process of reviewing, and I will respond to probably right after this meeting, at which point I think we will publish, I said -10, but maybe it's -11. I don't remember the exact version we are at right now. So that should hopefully address all the outstanding comments that are there on the draft. So that's pretty much the status.
Okay, I think you're right. It is actually I think -10 is actually posted right now, and the next will be -11. Anybody have any questions on this? Not hearing anything. One more status slide, which is on milestones. So despite my best efforts, we still have all of our milestones completed. As I suggested adding some, and after discussion, we added one for the IPv4 by IPv6 submission to the IESG, but we've done that now. So it's still the case that there are no official milestones for the group that haven't been accomplished. So that's the current status. Unless somebody wants to bring something else up, I will go ahead with the slides for Let's Rely Babel RTT.
Can you hear me?
I can.
Good. Okay, so hello. I'd like to tell you a few words today about Babel RTT, but before I'd like to thank Donald. I was at the mountains this morning, just packing to take my train back to Paris when I received the reminder from Donald telling me you didn't send your slides yet. So thanks a lot for the reminder, Donald. You saved me from having egg on my face. So let's hope it goes well. I prepared the slides today. Next, please. Next slide, please. Yeah. So in this working group, we have had a policy, and I think we can all be proud of this policy. We have had a policy of having of implementing everything we did. That allowed us to catch quite a few things that seemed obvious but turned out to be difficult to implement. We didn't make these mistakes. And the other advantage is that we know which of the things that we've been working on are useful. So all of the extensions that we've made to the core Babel protocol have either are in the process or have been standardized, or are not actually used in production. So for example, there is one extension that I'm very keen on, which sounded like an excellent idea, and it turned out not to be useful. That was the radio diversity extension. It's still in the Babel V code, but it doesn't improve things in any reasonable topology. It's a big surprise. I want to understand why. I don't currently understand why, but it's just not useful. So we're not standardizing it. Another example is TOS specific. So having different routes for different types of service intuitively sounds like something useful. But in fact, nobody has requested the feature. So there is code somewhere in a Babel D branch. I'm waiting for people to request it. Nobody is requesting it. We're not normalizing it. There's one exception, that's Babel RTT. Babel RTT has been used in production for 7 years now. It's been requested. Is Ronald here today? Yeah, I see with pleasure that Ronald is in the room. So Ronald has been telling me that it needs to be standardized, and I think he's right, because people are actually using it in production. And it's only described in an expired IETF draft and a paper that got, a scientific paper that got rejected. And you know, people always give you long explanations. The referees didn't get it, and so I'm the main author of this paper, and I can tell you on authority that it was not a very good paper, and it was rejected for good reasons. Next, please. Okay, so quick history. It solves a problem that I'm going to remind you of, in that Nexedi noticed, a company that is using Babel in their overlay network, in early 2014. So I spent part of the spring of 2014 designing the solution. Then I found a rather bright student, Baptiste Jonglaise, and Baptiste Jonglaise implemented and wrote it up together with me in the summer of 2014. So that was the original internet draft and the paper that got rejected. It got deployed in production during the autumn of 2014. And finally, after Ronald prodded me a few times, I think Donald also insisted, I presented it to the working group in March 2019. But the main point is that it has been continuously deployed in production for 7 years. And here are the references of the 2 places where it's described. Next, please. Okay, so I've already told that back in 2019. I'll be very quick. Nextd are running a global overlay network. They have a few hundred small data centers, and they're running tunnels between them, and they use Babel to route over them. Now, this is a typical topology. They have 4 data centers, Lille, Paris, and Marseille, all of those in France, and 1 in Tokyo. Now, in this topology, what happens when the Lille-Marseille link goes down? Well, Babel sees 2 hops between Lille, Paris, and Marseille, and 2 hops, Lille, Tokyo, and Marseille. And non-deterministically, once in 2 cases, it will route the packets through Tokyo. So you might say, but we thought that Babel was able to use flexible metrics. Yes, but here, the links are lossless, so Babel just sees 2 hops in every case. And Nextd were not happy with having their traffic go through Tokyo whenever there was a failure. Next, please. So my initial idea would be to put a GPS in every data center so that we would use real-world distance. And apparently that's not practical. The problem is not the cost of the GPS. The problem is that you need a technician to maintain the GPSs, and that makes the cost prohibitive. Another suggestion was to use geolocation, but there are 2 problems with that. First, geolocation is not very reliable. And second, you have a bad mixture of layers when you use geolocation to do routing. And you have layering violations, and that makes everyone nervous. So the idea was to measure the RTT, the 2-way delay, and derive a metric from that. And if you do it, it seems like a simple idea. But the first point is that the natural way to measure RTT requires an asymmetric and synchronous interaction. Now, Babel is a peer-to-peer, completely symmetric protocol, and it's asynchronous. You can always delay sending of a packet by up to a few seconds. And the other thing is that if you use RTT as input to a routing metric, if you're not careful, you're going to have a negative feedback loop. And when you have a feedback loop, you end up with oscillations. Next, please. Okay, so so now I've come to the first part. What is wrong with measuring RTT in the naive manner? The natural way to measure RTT is to send a ping packet in the client to server direction, and the server replies pong as fast as possible, and you measure the difference between the time at which the ping has been sent, which I note TO for origin, and T, the time at which the pong is answered. Okay, that's what you do. That's very simple, but this is a asymmetric protocol. It's client-server, and it's synchronous. The server has to reply straight away. So in Babel, we never have situations in which we have to reply straight away, and that will break all the scheduling in your Babel implementation. Next, please. So looking at the literature, I found a very nice algorithm, which I call Mills's algorithm, because it's due to Mills, but I don't think it really has a name. And it was used in an old routing protocol that I think nobody remembers anymore, even though it's pretty nice, called Hello. And it's also used in NTP. So the idea is that instead of sending just a ping, you send a packet that contains, so look at the second packet here, what you get, the second packet, the one that goes from right to left, this packet contains 3 pieces of data. TO, which is the origin timestamp, is the timestamp of the previous packet that was received by the sender. TR, the reference timestamp, which is the time at which the previous packet was received by the sender. And TT, which is the transmit timestamp, the time at which this packet is being sent according to the sender's clock. And then the receiver receives the packet at time T, and it computes t minus to on the left-hand side, minus the time during which the packet was being in transit at the sender, which is tt minus tr. So what you can notice in this formula is that you only subtract either the clocks on the left-hand side or on the right-hand side. And so that means that the clocks don't need to be synchronized. And the other thing is that you can dwell as long as you want between tr and tt, as long as the clocks don't drift too much from each other. So it's a symmetric, asynchronous algorithm. It doesn't require clocks to be synchronized. It's something that fits well with Babel. There are only a few things that you need to be careful with. Next, please. Okay, so Babel always has this problem that all the algorithms need to be adapted because it uses both multicast and unicast. So we have split the 3 timestamps into 2 groups. The transmit timestamp is conceptually multicast, so we start in the hello, and the other 2 timestamps, the origin and the reference, are conceptually unicast, so they are stored in the IHU. So the IHU in Babel can be sent over unicast or multicast, but it's conceptually unicast, and IHU will be ignored by everyone except the receiver. And originally we started with 10 millisecond timestamps, and then Dave yelled at us saying that if you define an extension, make it future-proof, and now we use timestamps that are that have a granularity of 1 microsecond. Next, please. Okay, here's the packet format. It's pretty obvious. We use a sub-TLV in hello and a sub-DLV in IHU. In hello, we have just 1 timestamp. In IHU, we have 2 timestamps. They are not the same. And there is one thing that bothers me about this encoding is that we use type 3 for both, and we disambiguate by looking at the type of the enclosing TLV. The question I'd like to ask to the group is, should we switch to using distinct types for the 2 kinds of timestamps? Next, please. Okay, so quickly, if you use RTT as a routing metric, you're going to have oscillation. So here, A is sending traffic to B, and the traffic goes through D, and then the AD link gets congested, the RTT goes up. So an RTT-based implementation of Babel is going to switch to the route going through C. Now, at this point, the process reverts. The route from A to C, the link from A to C gets congested, so the RTT increases, and we switch back to AD. We're going to have oscillations. Now, Babel doesn't care. It still maintains loop-free paths. However, when you have oscillations, you might have packet reordering, and that's going to destroy the performance of TCP or of your video conferencing application. Next, please. So what we do in Babel D is that we have a complex process. We don't use the RTT values immediately as metrics. We take the RTT samples. Yeah, we use the RTT samples. We smooth them. We get a smoothed RTT. Then we map it using a nonlinear map to a value that we call the RTT-induced penalty. And then we compute the link cost as we usually do. You add the link cost to the penalty. You get a metric. And even then, you don't use the metric immediately. You apply some hysteresis to the metric in order to get route selection. And with all of this, it works pretty well, but we don't have a theoretical understanding. Basically, we've hacked this together. It works beautifully well, even in the worst cases that we try to design in the lab, but we don't have a theoretical understanding. We don't know which of the bits here are necessary and which are just to make us comfortable. Next, please. Okay, so Babel RTT right now is, to my knowledge, the only widely deployed Babel extension that is not in the process of being standardized. There are good reasons for that. It is a simple algorithm, but it's a simple extension, but it's difficult to design the algorithm that make it work well. And we don't understand the algorithm that we've designed. So what I'm planning to do is to revive the draft, which I promised 2 years ago, but things have happened since then. And because we don't have an understanding of the algorithms, I propose that it remain an experimental RFC. If you disagree, please object now. And if you do agree, please review the document when I get around to publishing a new version. Thank you for your attention.
Thank you. Comments, questions, whatever. Not everybody is clamoring for the floor. I guess I would say you should probably use different types, as you asked, but
I should, excuse me?
I think you should use different types for the sub-TLVs, and that it would just be clearer that way. And I think experimental is a fine category, but others may have other opinions, and it's up to the working group.
So there is some argument in favor of keeping it compatible with the installed base. If we use different types, then we will want to be able to attach. The nice thing with the current encoding, the reason I hesitate, is that it makes it very clear where the sub-DLVs are allowed, only in hello and IHU. If you start having timestamp sub-TLVs that are generic, that has different types, people will be tempted to attach them to other packets. And I'm afraid that once people start doing that, it will cause interoperability problems. So the fact that you use the same type means that you really need to, they are strongly correlated with a single TLV, and it gives less liberty to the implementer to do the wrong thing. So I'm not saying, I'm playing devil's advocate here. So yes, I agree with you on the one hand, it makes me uneasy to use the same, to overload the same type. On the other hand, there are some technical reasons to do the opposite. And I mean, I've had, I keep oscillating between the two opinions.
Well, compatibility with working code is a strong argument. Dave in the chat says he believes they should stay the same. So.
And Ronald is telling me not to listen to him, but it's too late now. I've already listened to you, Ronald. You should have warned me earlier.
Okay. So I think that there's been substantial evidence of interest in this in the working group and at the meetings in the past and on the mailing list in the past. So seems like a good idea to me. Well, if there are not anybody who wants to speak to this, I will proceed to the next item on the agenda. All right, so this is something that I thought might be of interest to people in this group. Ended up being kind of a fairly general presentation on 802.11 frame formats and addressing and transit links, which are a fairly recent feature, and mesh, and touches a bit on multicast and mesh in 802.11, which is Wi-Fi. So it's very complicated, and I'm just going to sort of forge ahead. People who want to interrupt a question, whatever, just raise your hand, whatever, or turn on the mic and speak. It's a very complicated standard. You can get a full copy. It's over 4,000 pages. So almost every option you can think of, and many extensions are all available. I'm just speaking for my opinions on things. I was involved in some of the 802.11 work, but that was a little while ago, so I could be wrong on some things. I won't go into detail, but this is listing some of the general features, including aggregation at multiple levels for data frames for higher speed, and when you have a less noisy link, a higher speed link, and fragmentation when you have low speed, more noisy links. Billions of chipsets are sold a year, so that 802.11 can afford to develop improvements and things which even are fairly maybe not major as minor improvements, because the cost of developing the improvement, incorporating in the chips, is amortized over such a large number. So I'm just going to initially talk about the infrastructure mode. Probably everybody's familiar with. This is kind of what people think about it, what it looks like. So you got like stations that are associated with an AP, an access point, and maybe there's some wired infrastructure. So that set of things is called a basic service set. That's identified by a BSS ID, which is 48 bits. This is all kind of layer 2-ish. So it's usually the MAC address of the AP. It could be something else. And you frequently have several APs with the same SSID, maybe even just in your house if you've configured them with, or at a business or something. And you can roam seamlessly between these different things in what's called an extended service set. And normally they all have the same SSID, or service set identifier. So looking at it a little bit more from the point of view of the logical structure in the standard, it really looks more like this. There's this mysterious thing called the distribution system, which is actually very lightly specified in the standard. Just its properties are specified. So when a frame comes in from the outside world, it logically at least goes through this portal thing, and the distribution system is what knows where all these different stations are, knows where the MAC addresses are and stuff. And or if you send a frame between two stations that are either on the same AP or on different APs, it's the distribution system that knows how that works. So like I say, even if you send it between two stations on the same AP, if you read the standard, it says at least logically it goes through at least a vestigial little loop through the distribution system that knows that it needs to be sent back out by the same access point. So one of the questions that comes up a lot in any form of 802.11 is the multicast reliability. So I just wanted to mention that all the features that 802.11 has, it has most of the features you might think of to make multicast more reliable, because the usual complaint is that multicast has one or another problems, which lack of reliability is a common one. So you can always use serial unicast, unless you're trying to discover new stations or something like a beacon, whereby stations can find APs, needs to use multicast. But you can use serial unicast for anything where you have an association or you know who you're talking to. Multicast tends to use the lowest common denominator bit rate. So it knows what the rates are that have been negotiated or are currently in use on the different channels. So it can find the lowest one. You can configure it to multiply transmit the same data. So, if it doesn't get through in one try, maybe you do 2 tries, it'll be more reliable. Normally, a multicast is not acknowledged, and unicast has acknowledgements and retransmissions by default sort of on the single link, but multicast doesn't. But if you want to, you can there's a scheme where you can have block acknowledgements. The problem with having acknowledgements is if an access point has 100 stations associated with it and it sends a multicast, you don't want to have 100 acknowledgements smashing back in. So you can have the acknowledgements be accumulated, and the access point can poll for the acknowledgements. So it gets a bitmap of what frames have been received and things like that. So it's going a little more into the structure of these frames that are used in Wi-Fi. Wi-Fi is very much oriented towards a single unified complex header with optional fields, which may be present or absent, and lots of flags and things, rather than using nested logical headers of different types. So you have frame control, and this is sort of oriented towards data frames, and there's a whole bunch of fields and a bunch of address fields. Notice that a lot of these have a potential length in octets of 0, means they may not be there. And sequence control and so forth, and I'll say what these are. And there's the actual frame body, and it ends with a frame checksum as a standard Ethernet 32-bit checksum. So, oops, sorry. So going back, what are these fields? So the protocol version is 0. So you might think, hey, Wi-Fi hasn't really radically changed their protocol, so that would always be 0. But no, there's actually because they sort of ran out of types and subtypes, there's actually a protocol version 1, which is really the same protocol. It's just other extensions in terms of control frames and management frames and other sorts of things like that. There's lots of types and subtypes. So this is really for data frame. Notice this distribution system is mentioned. There's the to ds and from ds bits. We'll talk a bit more. More fragments is pretty obvious. If it's fragmented, that indicates there's more. There's a bit to indicate that this is a retransmission due to the link level acknowledgement and retransmissions. There's a power management bit, which indicates things are going on with various forms of power save and sleep modes. The more data bit is only used for certain special modes. Protected frame indicates that you have an encrypted frame body. That's a hop-by-hop basis of encryption, of course. And HTC is a high throughput control, means there's more other fields following this that have information about how the high throughput is happening. So what are these to and from distribution system bits? If they're both 0, it means they're really not part of this kind of infrastructure or mesh. Maybe you're what's called ad hoc mode or vehicular, where you're just sort of blasting something out to be seen. If it's has the from distribution system mode and not to, it means it's the access point is sending something to a station. The other way around, it means a station is sending something to an access point. And if both are on, you have a transit link, and that's kind of a really new 4-address mode that I'll be talking more about. There's a sequence control field, which is always present, and it has the fragment number for fragmentation and a sequence number. So there's actually 4 priority classes for QoS frames, and you have a separate sequence numbers in each class. So that way, if, for example, the link level acknowledgement is lost and you retransmit it when you didn't have to, so the other end gets 2 copies, I can see the sequence number has been duplicated within that priority class. And it'll know to, and if it, on the hand, if there's a missing sequence number, you could tell something wasn't there, but there's no actually no way to explicitly request retransmission in that case. Let's see. So these are what the various address fields are in these various cases, and you'll notice that the first address and the addresses fields 1, 2, and 3 are always present, and the first address is always the radio receiver, and in some cases that's the station, in some cases it's the access point necessarily, and the second address is actually always the radio transmitter, and in some cases that's also the access point of the station. However, in this transit through mode, the receiver and radio receiver and transmitter may be different. From the source may be different from the transmitter, and the destination may be different from the receiver. And you don't really need the 4th address in these cases. One thing in 802, the destination address appears first, as opposed to the IP protocols, which are from to. As the source address appears first. And usually it's better for the receiver address to appear first. If you're trying to do cut-through routing or something, you want to get the receiver address as soon as possible so you can start figuring out what to do with it. In fact, it's arranged, of course, with 802 addresses, such that the very first bit you get of the receive address is the bit which indicates whether it's unicast or multicast. So absolutely, as early as possible, you have information as to how to handle this frame, because frequently unicast and multicast are handled by significantly different methods. So I want to talk a bit more about this 4-address transit mode, which allows you to use a connection as a through link in a more general network. So here's, for example, so here in the middle, we do have an infrastructure, an access point and some stations associated with it, but we can send frames from a source that's sort of behind the access point, which is normal. There's normally a network, or at least the whole internet maybe behind the access point. We can send that over this infrastructure link to some destination that's behind the station. So you can have a whole general network, and the MAC addresses are all visible. This is all layer 2. So you can have the source, transmitter, receiver, and destination address be different. Or it could be between a source behind one station associated with the access point to a destination behind another station associated with that access point. So, and looking at it, again, essentially the distribution system that existed before, when you're using this 4-address mode, what you really have is a bridging conformant network. Because all the MAC addresses are visible, and everything in these links are essentially looking like they're Ethernet links in the 4-address mode, transit through links. You really just need, the distribution system is replaced by a sort of bridging conformant network, and you have one of those behind any 4 address supporting APs, and also behind any stations that support 4 addresses. You can also have classic APs tied in, or and you can have multi-drop links or single end station. Then you can also have classic APs associated with a 4 address AP. So the 4 address AP also has backward compatibility, so it will support classic stations that don't understand the 4 address mode. Now, all this shows everything is kind of tree-like. In fact, there could be networks at the bottom of this interconnecting these various behind the bridge state network. So you have a whole nother network down there. So looking a little more closely at what's going on between an access point and the stations, this 4 address transit link mode tries to treat the associations between an access point and various stations as much as possible as if they were separate point-to-point connections, even though physically you have the AP as a radio transmitter and an antenna, and when it sends something out via radio, it gets to all the stations. So the reason it wants to treat it this way, first of all, the stations may not see each other, so there's some danger in treating it as a multi-access link, but also all the IEEE bridging protocols, which are being used sort of as the back-end infrastructure for this, work better on point-to-point links, including, for example, spanning tree and stuff like that. And it turns out that this is actually necessary if you're going to use something like spanning tree or spanning tree itself for loop suppression in the general case, and also necessary to support the Ethernet requirement that when a station sends a frame, it doesn't ever get back to that station. It doesn't ever automatically, it never receives a frame that it sends, which is one of the basic fundamental assumptions of 802 Ethernet. So here's similar to the previous diagram, except that there are now these wired networks behind the AP and the station, and they're hooked together through an arbitrary network, which could hook to the internet in various ways, for example. And the way that spanning tree works is it breaks loops by somewhere along the loop. The way spanning tree works, it ends up inhibiting a port. So effectively turns off one of the links by inhibiting a port. And unless you do a lot of further monkeying around, which wasn't done for this standard, spanning tree might cause the access point to want to inhibit one of these links or more of these links down to the stations. So it has to sort of be able to treat them as separate ports. So for this transit link mode, even if it's being used on infrastructure links like this, there is a special mode for multicast. If it's unicast, it's pretty easy to treat these things because they really are effectively point-to-point. With the transmitter address and the receiver address, things just go between between particular antenna, one antenna and another, so to speak. And the other stations will ignore unicast frames that are not addressed to them. But if the AP is sending a broadcast frame or multicast frame, there's actually a special form of receiver address called a synthetic receiver address, or SINRA, where it can basically create a bitmap of which stations it wants to go. Now, of course, this is encoded into a 48-bit MAC address. So there's obviously not enough room in there to actually have a full bitmap if you have enough stations. You have 100 stations associated with an AP, which is certainly possible. You can't do that. So you either have to have multiple synthetic receiver address transmissions for different parts of the bitmap space, which is essentially the space of association identifiers, or you can also use serial unicast, but that would take a long time if there were a lot of stations. So that's how that has gotten to work. And similarly, you could have complicated cases. There could be a multi-destination source in the network on the right here, and it could send when it sends a frame out, it could end up, depending on where the loop's been broken, either going upwards and through the AP, or it can go down the bottom, or it could go both ways. And the loop has to be broken somewhere along here, and to make sure that the frame never gets back to it, and so you don't have indefinite looping frames. So when a frame is sent by a station to the AP, AP wants to be sure not to send it back to that station. And it doesn't have to worry about that in the simple 3-address case, where you just have regular frames and the stations are endpoints. There's nothing behind them. Because in that case, when a station sends a multi-destination frame to the AP just blasts it out to all the stations. And when that station gets it back, it does get it back, but in this case, it's okay because it can recognize itself as the source address. But when you have possible sources behind that station, it can no longer use that. And it doesn't even help to try to remember them and discard an identical frame, because the frame, there can be reconfigurations of the network that occur between sequential identical frames, so you can get the same frame from different directions. And really, the AP just has to know. The AP is what knows what's going on, and it has to be able to decide not to send it to certain stations. So I'm going to talk a bit about mesh, and then all the things we were talking about before, concentrating on infrastructure mode. The links were not particularly symmetric. I mean, the AP and the station are really different in a variety of ways. So with mesh, that's not particularly true. They are peer-to-peer, and all the mesh stations that can see each other and that have matching mesh profiles end up peering with each other. And mesh profiles identified by a mesh ID, which is in binary the same sort of thing as an SSID. Both mesh IDs and SSIDs are just strings of up to 32 octets of arbitrary binary junk. Of course, SSIDs are normally printable characters, but in the protocol they can be anything binary. But the SSID is not used for mesh, but the mesh ID is used instead. So it turns out that because mesh came along later, all mesh data frames are required to be what are called QoS frames. So QoS frames basically means you support this priority feature in 802.11 and stuff like that, which really almost all modern uses do. And this is one of those things people argue about in 802.11 is when can the support of non-QoS frames that don't support this be removed from the standard? And someday no doubt will be. But anyway, because that's true, there are some bits available in the QoS control field. And so those bits are used to indicate that it's a mesh frame. And if those bits are set to indicate that it is a mesh frame, then the mesh control field is added. So that's this extension field shown here, which this is number of octets across the bottom. And this is really sort of more of the header. It comes right after the header I was talking about and showing you previously, but it's logically considered to be part of the frame body. And the only real difference that makes is that it's subject to this hop-by-hop encryption over the air, which is just easier to implement that way. So what are these different fields in here? The mesh flags are really just used to indicate whether the addressing extension fields are there or not. TTL is a true TTL within the mesh. And this is unusual. 802 generally does not have TTLs. They've added an optional one in Ethernet, an optional Ethernet header recently. But at least it used to be the attitude in 802 that if your protocol needs a TTL, it's broken. That's just what they thought. So that's kind of their particular thinking. But mesh in Wi-Fi has always had a TTL from the start. And then there's this mesh sequence number. So the first mesh node, if it's sourced inside the mesh, then it's the place where the frame is sourced. If it comes from outside of the mesh, go through the mesh, then the first mesh node it hits adds a sequence number to it. So every mesh node is required to keep a cache of recently seen mesh source addresses and sequence numbers. And if it receives a frame which is a duplicate of one that it's forwarded before, it discards it. And that's basically how with the TTL, how it saves itself from loops and things like that. So from an external point of view, the Wi-Fi mesh just appears to be a single multi-access link. It can have multiple connections to the outside world, or it could have no connections to the outside world. So all of the stations, for example, the ordinary end stations hooked to any of the mesh nodes in the connected mesh can all see each other as if they were all hooked to a piece of old-fashioned coaxial Ethernet with multi-taps on it or something. And the mesh stations can also be access points, and they can be mesh gates to connect to other networks, and they can also even be portals, gates and portals to connect to outside networks like the internet. So this address extension column on here, fourth column, is these bits in the mesh flags. And so the simplest case, let's say we have a mesh data frame, a unicast frame is all internal to the mesh. So as it hops along, in the general case, there's the receiver and transmitter. There's also the source and destination. The source and destination in the mesh. You don't need anything else. It just uses 4 addresses to hop along there. Somewhat like the transit link case, but this is the peer-to-peer mesh case. On the other hand, if the frame originated or terminates outside of the mesh, then you need some more information. It has the receiver and transmitter on each hop. It also has the mesh, the final mesh node, the mesh destination address, and the first mesh node, the mesh source address. But if these are out from or two outside the mesh, there's also the true original source outside the mesh and the final ultimate destination outside the mesh. So if the frame happens to be multicast, you can simplify this quite a bit, because you don't need to individually address the receiver in general, because the receivers will respond to any multicast frame as long as they're from somebody they're paired with. So in this case, the receiver addresses can be the ultimate destination address, because it's this really a multicast group. You do still need the transmitter and the source. So if it is originated inside the mesh, you have the next to the bottom line case. And actually, in that case, you can actually omit the 4th address. It just needs 3 addresses in that case. And if it's originated from outside of the mesh, then you need to have not just only a mesh source address, which is the first node in the mesh that the frame hit, but also an ultimate source address. So in the general case, these mesh frames have 6 addresses in them, all MAC addresses, all 48-bit MAC, and it's all layer 2. So, here's some ones. I don't know that I want to go through these all in detail. It'd be a little tedious. Basically, what the addresses look like if you're doing a single hop inside the mesh. First was like from 3 to 6, and which is really simple in the mesh, because some of them, a whole bunch of the source and transmitter addresses are 3, destinations are all 6. Then we have multi-hop, so you have 2 lines, and the transmitter and receiver addresses change, but the source and mesh source and destination and mesh destination all stay the same. One more slide of this. So in this case, if you have one going from 14 to 4, it gets 14 to 1. This is a wired Ethernet. I don't have a line for that. But from 1 to 4, it says a source address outside the mesh, but the mesh source is 1. And in that case, the transmitter is also 1. And then you have everything else is 4 for the receiver. And the last case is one going from 14 to 12. So it goes through the mesh, and it shows via 3 and 6. And this shows all the different states it goes through. So you have to, so loop prevention is sort of handled in somewhat different ways in different regimes. If you have this mesh in the middle, layer 2 mesh, but you have the outsides are connected into one larger network, then, and this is all layer 2, I assume there are no intervening IP routers, then that's the first 2 points here. The loop prevention inside the mesh is handled by the TTL and by the duplicate discard, essentially. So meshes sort of succeed in handling Wi-Fi meshes, this multicast distribution, by just sort of flooding it and discarding duplicates as it goes along. If you're considering a larger layer 2, which incorporates the mesh will just appear to be a simple link in it. So in this larger network, there's standard short loop prevention algorithms, a spanning tree or the like, will break the loops. And of course, if you get further out to IP routers, like that terminates the layer 2 fabric, so to speak, whatever. And if you're wondering about loops that are in the layer 3 space beyond IP routers, then that's really a function of your IP routing algorithm to solve. So that's what I had. I thought this might be of some interest to people in this group. I hope it was. Julius, go ahead.
So could you please go back to the slide where you showed the 3 and 4 address formats, just in the plain 802.11 case, not in the mesh case?
Sure. If I can find that.
It was in the early teens. I think it was 12.
There's one. There's also
Yeah, that's
another.
very good. That's very good. So
Okay.
the natural question one asks, when you see this, the natural question is, why does Wi-Fi need to have up to 4 addresses when we've been doing fine with just 2 addresses, both in Ethernet and an IP?
Well,
And yeah, go ahead.
oh, I would say that if you have the thing is to usually have in that case a couple of layer 3 addresses, and then you have the MAC addresses on the link. So it's just that you have 4 addresses that just aren't all the same kind.
Yeah. So what's going on here is that Wi-Fi is doing routing at layer 2.
Oh yes.
Okay. So the way
yeah.
I understand this is that Wi-Fi is actually doing tunneling.
This distribution system here, the distribution system here is that magically does routing, and it's the standard very carefully doesn't say how it does it or anything at all. It just gives the properties of it, so you can implement the distribution system however you want, and different commercial products that support ESSs, so you can, seamlessly roam between these APs, do it in radically different ways.
So and now there does exist an opinion that routing belongs at layer 3, and that once you start pushing routing to layer 2, you are going to have ever increasing complexity, because doing routing at layer 2 is difficult. And if you look at your slide, I think it was 24.
Let's see here, 20.
Well,
That's
once
24.
once you start wanting to do routing, you want to do more general routing at layer 2. And now you end up suddenly with 6 different addresses.
Yes.
So one opinion would be, why don't we do routing at layer 3 as we always have done? Okay, now...
Well, you're not going to do that in 802, so if 802 is writing the standard...
Of course. But I mean, I'm not an 802 member. I am trying to to solve problems in the right way. There is a beautiful talk by Radia Perlman about Trill. So Trill does some very complex routing at layer 2. I mean, whether it's at layer 2 or not is a matter of opinion, but
I would say, well, I think it's you can easily argue it's in between 2 and 3, but it does root on MAC addresses. So it roots on layer 2 addresses, and in my opinion, it's just IS routing. It happens to be, instead of on IP ranges and prefixes, it's flat MAC addresses that are being routed on.
And in this talk, she starts her talk with this beautiful introduction saying, I think that routing should be done at layer 3, but people want to do it at layer 2 and they're doing it wrong. So I'm going to design a protocol so that at least they can do it right. Okay.
Yes, something like that. Yeah.
Yeah. And I'm paraphrasing from memory here.
Yeah, I understand.
And so the real question is, why do people want to root at layer 2? So my analysis would be that there are 2 reasons why people love layer 2. One is that configuration is easy. Configuring Ethernet switch, compare configuring an Ethernet switch, an unmanaged Ethernet switch, with configuring an IP router. Mm-hmm. So I think that the original sin of us layer 3 people is that we made configuration uselessly complicated. And that's how I got interested in the HomeNet project, in the HomeNet working group. So the reason I'm at IETF today is that 10 years ago, some wise people told me, go and look at HomeNet. It's interesting. Unfortunately, HomeNet appears to be moribund now, but I still think that the basic idea of allowing people not to root at layer 2 by giving them easier configuration at layer 3 is a sound one. And the other reason why people want to do routing, and that's very relevant for Wi-Fi, is that if you do your routing at layer 2, then you get mobility. You get roaming between access points for free. Okay, one thing
Right.
that you
Another
didn't
example, this
mention
is-
because it was obvious for you is that the distribution system handles mobility of they're called stations in 802.11 because they
Right.
move, right?
Another example of something that handles mobility is the 5G core or other mobile phone
Yeah.
system.
Yeah, I was coming to that. So I've been working before the first lockdown happened on a distribution system on Wi-Fi that used principles similar to what is being done in 4G. I don't know what is done in 5G, but what is done in LTE. And I reached the point when I had a prototype that worked in my limited testing, and then lockdown happened, and I found it difficult to motivate myself for mobility while in lockdown. So that's something I need to come back. And interestingly enough, it's when you use Babel as the distribution system, it turns out, well, now quite unsurprisingly, that you only need the to-address format. So my hypothesis that the reason for which you need multiple addresses is that you're doing routing appears to be validated by the fact that when you do your distribution system at layer 3, then you no longer need the multiple address formats. Okay, so the thing is called sround.
Okay.
The code is available as you can get it by doing git clone, so it hasn't been described yet. I've announced it on the Babel users list, but not on the Babel at IETF list. And you can get it by doing from memory. And I plan to get back to it as soon as I can, as I'm allowed to move once. Now that I'm allowed to move once again, I want to get back to it and work on it.
Okay. Unfortunately, this is very interesting, but we are kind of out of time for this session. So I don't know if we should. And wanted to thank everybody for, let's see, actually, I'm going to go here, calling in, and people should comment on the mailing list and whatever. And, we can see you at the next IETF meeting, I guess. And if we have a topic for which we want to make more rapid progress in discussions in the interim, we can schedule interim meetings before then. But so thanks everybody, and talk to you later and see you on the mailing list.